Hi, everybody. So now let's look at some really fundamental examples of matrix groups, which if you continue in any kind of scientific field, there's an excellent chance you'll see some version of these groups again. So the first one is a generalization of a group that we've looked at a lot. We talked a lot about the 2x2 matrices with non-zero determinant, and we called that group GL2 of R. There's a general version of that called the general linear group GLN of R, and it has three equivalent definitions. So the first definition is that it's the group of bijective linear transformations from Rn to Rn with the group operation given by composition of maps. So you recall that we defined the permutation group on a set to be the collection of just bijective maps from the set to itself. And we showed that under composition, they form a group. Here, we're taking not every map from Rn to Rn, but every linear map from Rn to Rn. But we're still using the composition of maps as our group operation. And the nice thing about that is that it makes it relatively easy to check that this is in fact a group. Because first of all, it has an identity element, namely the identity linear transformation. The identity map is linear, and so we have an identity linear, that's our identity map. Because if we have any linear map, let's call it, I don't know, U composed with the identity. Let me use I for the identity, because that's a nicer way. U composed with I of x is U of x. And so the map U composed with I is the same as the map U. And similarly, I composed with U of x is I of U of x, which is U of x. So I composed with U is U. So I acts like an identity. What about inverses? Well, we talked in the review of linear algebra that if you have a linear map which is bijective, the inverse map is automatically linear. And so if we have a map T from Rn to Rn, which is bijective, then the inverse map is also in GLNR because it's also a linear map, and it functions like an inverse because T composed with T inverse is the identity, is T inverse composed with T by definition. And then finally, we have to check associativity, but composition of maps is always associative. I mean, T composed with U composed with V applied to X means T composed with U applied to V of X, which means T applied to U of V of X. But that's the same thing as T composed with U composed with V of X. So this definition makes it very kind of formal to show that this is a group, but buried in here is the fact that the inverse of a linear transformation is linear, and to show that we actually had to do something with matrices. Well, the equivalent definition is that it's the group of invertible n by n matrices with matrix multiplication. And why is this an equivalent definition? Well, we showed that there's a correspondence. Every linear map T comes from a matrix A, where T of x is just matrix multiplication AX. And T is invertible means the matrix A is invertible. And composition, T composed with V, corresponds to matrix multiplication A times B if V corresponds to the matrix B. So if we think about this in terms of just reinterpret everything we know about linear maps in terms of matrices, then to say that we have an invertible n by n matrix and that the operation is matrix multiplication is basically the same thing as saying we have an invertible linear transformation and the operation is composition. So that gives us a concrete version of GLNR. So it's very much like GL2R, but for 3x3 matrices. So an element X we can think of an element in GL3 of R as just being a matrix that's invertible. I don't know, 3, 0, 0, 0, 1, 5, 0, 2, 4. That would be an example of an invertible 3 by 3 matrix. And a final definition is we can use the fact that we know that a matrix is invertible if and only if it has non-zero determinant. And so we could define GLNR to be the group of n by n matrices with non-zero determinant. And so those are three different ways. And of course, we worked a lot with GL2 of R, and we defined it to be the collection of 2 by 2 matrices with non-zero determinant. And so it's a special case of this definition. So the general linear group is the group of all linear transformations of Rn. So you may recall that we also talked about SL2R, the special linear group, which was the subgroup of SLNR, sorry, the subgroup of GLNR consisting of matrices of determinant 1. And we can do that for GLN for the n-dimensional case as well, and we introduce the special linear group to be the subgroup of GLNR consisting of matrices with determinant 1. And so it's just like SL2R, but for n by n matrices. And the group SLNR is a normal subgroup in GLNR, and the quotient group is the multiplicative group of real numbers. And this is obtained by the first isomorphism theorem. Because we have the determinant is a homomorphism from GLNR to R star, because the determinant of the product of matrices is the product of the determinants. And that's the first point. The second point is that the determinant is onto, it's surjective. And to show that, we just have to prove that we can get any non-zero number as a determinant of a matrix. And we can, because if we take the matrix R1, 1, 1, call this our matrix A, then the determinant of A is R. So here, as long as R is not equal to 0 and as an element of R, then we can make it the determinant of a matrix. And finally, the kernel of the determinant, by definition, is SL2R, SLNR. And by the work that we did on factor groups, we know that kernels are automatically normal subgroups. And the first isomorphism theorem says that if we take GLNR and we map it to the quotient group GLNR mod SLNR, and we take here the determinant to R star, that the first isomorphism theorem says that there's a bijective map between this quotient group and the image of this map determinant, but the image is all of R star. So there's a bijective group homomorphism here. So GLNR mod SLNR is isomorphic to the multiplicative group of the reals, just like for GL2R mod SL2R. Okay, now let's look at what are called orthogonal matrices, and this will lead to another kind of matrix group called the orthogonal group, which is the group of rigid motions of space. So whereas the general linear group is all linear transformations, now we're going to look at matrices which preserve the distance between points. And so we're going to introduce that as a condition, and we're going to say that a matrix A is called orthogonal if you take any vector x and you apply a to it and you look at its length, then that doesn't change. So the classic example in the plane would be a rotation, where you take a vector and you rotate it through an angle theta, but you don't change its length. And in 3 dimensions, the same thing could happen. You take a vector starting at the origin and you rotate your vector space, and the length of the vector doesn't change. And any matrix where the associated linear transformation has this property is called orthogonal. And it turns out that we can describe orthogonal matrices as being all those matrices whose, well, it can either be that its rows form an orthonormal set, or its columns form an orthonormal set, or it satisfies this property that A times its transpose is equal to the identity. And actually, it's also the case that it could be that A transpose times A is equal to the identity. All of these are the same. So let's start by assuming, so we need to prove this if and only if thing. So let's first assume that A has this property, that the norm of ax squared is the norm of x squared for all x in Rn. Well, in particular, that means that the norm of AEI is equal to 1 for I equals 1 up to n, because the basis vectors EI have length 1, so AEI, the norm of AEI squared must be length 1. And remember that AEI, if you think about the matrix A, AEI, the coefficients of AEI are just the ith column of A. Because when you multiply your matrix, here it is, A11, A12, dot, 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 A1n, A21, dot, 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 out to A2n, so forth down to ANN, and you multiply that times the vector which just has a 1 in position I, each time you take a row and multiply it times this thing, you just are picking out the ith element in that row, which is the ith column, the entry in the ith column. So this is actually equal to A1i, A2i, down to ANI. But if the norm of that is equal to 1, that means that that column is a unit vector. So this shows that the columns of A are unit vectors. What about, how do we know that they're orthogonal? Well, for that, let's look at A times E I plus EJ. So what is this? This is the dot product. It's AEI plus AEJ dotted with AEI plus AEJ. So it's got AEI dotted with AEI. That's what we were calling AEI squared. And then it's got twice AEI dot AEJ. And then it's got AEJ dotted with AEJ. And what do we know here? Well, we know that this is equal to 1, and we know that this is equal to 1. But we also know that this is equal to, if A is orthogonal, to the norm of EI plus EJ. And that's equal to 2, because it's equal to EI dot EI plus 2EI dot EJ plus EJ dot EJ. This is 0. These are both 1. So we have 2 equals 1 plus this middle term. So that middle term had better be 0. And we get that AEJ dotted with AEI is 0. And that means that the jth column and the ith column of A are orthogonal. So if you put these two things together, we've shown that this property implies that the columns of A are orthonormal. Well, that means that if we take A transpose, which remember looks just like A, I'm going to do this. Let me call the columns. Let me write A so that the columns are sort of A1, A2, A3, out to AN. So A transpose, the rows are A1, A2, out to AN. And when you multiply A transpose times A, you've got the rows times the columns here. And because this is an orthonormal set, this is going to be the identity matrix, because the first row dotted is going to get dotted with the first column, and that's going to give you 1, but then the first row gets dotted with all the other columns, and those are zeros. And similarly, the second row gets dotted with the first column, but that's 0, but then with the second column, and that's 1, and so on. So this is equal to the identity. So we've shown at this point that if norm ax squared equals x squared for all x, then A transpose A is equal to the identity, and the columns of A are an orthonormal set. But this condition tells us that A transpose is equal to A inverse, right? I mean, A is clearly invertible, and its inverse is A transpose. And now let's multiply on the left of this equation by A, and we get A transpose equals the identity. And if you go back through this, this tells you also that the rows of A are also orthonormal. So we've shown one direction of our if and only if proposition, namely we've shown that if the matrix is orthogonal, then A transpose is the identity, and the rows and columns of A form an orthonormal set. What about if we go in the other direction? So suppose A transpose equals the identity. So we want to know, what is the norm of AX squared? Or what is the dot product of AX dotted with AX? And here, I'm going to use another algebraic version of the dot product, which is that if you have two vectors, one way to think about the dot product, if V is a column vector, V1 dotted down to Vn, then one way to think about the dot product is that you can take the transpose of V, which is the row vector V1 up to Vn, and then do matrix multiplication, transpose of VV, to get the dot product V dot V. And if we use that a point of view to do this calculation, then what we're doing is we're taking the transpose of A of the vector AX and multiplying it, doing matrix multiplication, and multiplying it times AX. But one fact from linear algebra, which I didn't prove, but which is true, is that if you take the transpose of a product, it's the product of the transposes in the opposite order. And this comes just from looking at the definition, the formulas for matrix multiplication, and looking at what happens if you reverse the indices. And that means this becomes X transpose X, transpose A, X. But A is orthogonal, so this is the identity matrix. So this becomes the transpose of X times the identity times X, or the transpose of X times X, which is the norm of X squared. So from this little linear algebra argument, we see that this condition that A transpose A or transpose A being the identity is equivalent to being a linear transformation which preserves the lengths of vectors. Now we can introduce the orthogonal group, and for that we need to know that it's a subgroup of GLNR. We need to check that it's a subgroup. For that we know that the identity is orthogonal because E transpose E is just E. E transpose is equal to E. We need to know that the product of orthogonal matrices is orthogonal. So we need to know that if A and B are orthogonal, we need to know is AB. And for that, we need to know whether or not AB transpose times AB is equal to the identity. And remember that AB transpose is, you reverse the multiplication and take the transpose. This is the identity because A is orthogonal. And this is the identity because B is orthogonal. So the product of orthogonal matrices is orthogonal. And then finally, what about inverses? Well, if A transpose is the identity, then we already know that A transpose is A inverse. If you take the transpose of both sides of that equation, you get that A is A inverse transpose, which is A transpose inverse. And so you see that, if we want to know if the inverse is orthogonal, we need to know is, maybe I'll do it this way. Is it true that I could make my life a little easier. Is it true that A inverse times A inverse transpose is the identity? And that's the same as A inverse times A transpose inverse, because transpose and inverse commute. And this is the same as A transpose A inverse, and that's the identity. Sorry for the mess there. But the inverse of an orthogonal matrix is also orthogonal. So the orthogonal matrices form a subgroup of the general linear group. And if you further restrict, and you not only require that the matrix be orthogonal, but also that it have determinant 1, then you get a group called SON. So S is sort of always the code word for determinant 1, consisting of orthogonal matrices with determinant 1. And just like we did with SLNR in GLNR, we can look at SONR in ON of R. And now we use the fact that the determinant of an orthogonal matrix has to be plus or minus 1. Because if A transpose is the identity, that tells you that the determinant of A squared has to be the determinant of the identity, which is 1. And so the determinant of an orthogonal matrix has to be plus or minus 1. Both are possible because this is an orthogonal matrix which has determinant minus 1, and the identity is an orthogonal matrix which has determinant 1. So just as we did in the SLN case, we can use the first isomorphism theorem, and we see that we have ON going on to plus or minus 1 by a homomorphism, because the determinant is a homomorphism. So if we take ON mod SON here, there has to be an isomorphism between this factor group and the image of this homomorphism, which is surjective. So the quotient group ON mod SON is just the group with 2 elements, corresponding to the multiplicative group with plus or minus 1. And just some examples, I've said this now several times, but SONR is the group of rigid rotations about the origin. If you throw in ON of R, you also include reflections. But SON is just rotations. We've seen SO2R many times. It's our cosine theta. It has many names. Cosine theta, minus sine theta, plus sine theta, minus sine theta, cosine theta. These matrices have determinant 1, and they correspond to rotations. SO3 corresponds to rotations of the unit sphere in 3 space.